Today, we're going to give an introduction to modeling by differential equations. Let's start with the motivating question. Using the demographic history of the United States, can we predict the size of the US population in, say, 100 years? Well, let's take a look at this historical data. Here we have a list of the census information that's posted online. Here you can see all of the data that consists of the number of people that have lived in the United States every 10 years, starting in about 1790. We started at roughly 4 million individuals, and in the last year that the information was posted online in 2000, we're roughly at 281 million individuals. In order for us to try to answer our motivating question, let's assume that the US population undergoes an exponential growth. That is, the size of the population at t years is a function of the form p of t equals to a constant p0 times an exponential e to the kt. If we take the logarithm of this function, then we see that the log of p of t is the log of p0 plus k times t. So the idea is that we're going to take the logarithm and then try to find these parameters lambda 1, which is the log of p0, and lambda 2, which is this number k. Here's the new data once we've computed the logarithm of our population data. As a reminder, we can perform what's called a linear regression. That is, given a list of data points, let's say ti, yi, then we can find that linear polynomial, which is the best least squares linear fit. We're not going to worry much about where these formulas here come from today. We'll just simply say that using the data that you see here on your screen, we can compute that lambda 1 is approximately negative 20.527, and lambda 2 is approximately 0.020. Now let's put all of this together and actually take a look at the plot of our function p of t. The blue dotted line you see here is the actual data from the census. The orange dotted line is the curve that we're assuming. This is our p of t. You'll see that there's some problems here. In particular, our orange curve really does not do a good job of matching our blue data. So what exactly went wrong here? Well, let's try to have some descriptions using either analytical methods, qualitative methods, or numerical methods. First, let's start with the analytical. That is, we want to try to discuss the equation which governs the situation. Well, by staring at the graph, we see that maybe perhaps our assumption of exponential growth is incorrect. Let's now move to our qualitative description. That is, we want to try to describe the behavior of the solution. Simply put, the solution that we have, our p of t, grows in a different manner from the data. Number 3, let's take a look at a numerical description. That is, somehow we need to perform arithmetic to find our solution. Well, in our arithmetic, we used a least squares fit. So maybe there could be an error in the least squares fit, or maybe perhaps the initial data is flawed. Either way, this is going to lead to another motivating question. Maybe the assumption of exponential growth is flawed, but how do we come up with the correct assumption? This is the idea here of the course. We're going to use calculus to build a mathematical model. To do so, let's first remind ourselves, what is the definition of calculus? Well, Wikipedia states that the word calculus is Latin for a small stone that was once used for counting. The Merriam-Webster dictionary defines calculus in a much different way. It states it as that science or class of sciences which treats the exact relations existing between quantities or magnitudes, and of the methods by which, in accordance with these relations, quantities sought are deducible from other quantities known or suppressed. Well, using this, there are several types of calculi. There's the differential calculus, the integral calculus, the difference calculus, and variational calculus. So the term the calculus is somewhat misleading because it actually refers to the differential calculus. Simply put, this is the science of manipulating differentials. So a differential equation is simply an equation that involves differentials. Um, You'll notice that we haven't really defined what a differential is. Don't worry, we'll come back to this and define this later in the course. Well, the differential calculus was more or less invented by the English mathematician Sir Isaac Newton. A lot of his ideas were written up in his big work, Principia Mathematica, which translates from the Latin to Mathematical Principles of Natural Philosophy. He wrote this massive work when he was in his 40s. Today, I'd like to discuss a few of the ideas that came out of this book. What we're going to do is try to use differential calculus to build a mathematical model. Let's start with the first idea. Perhaps you're familiar with Newton's famous equation F equals ma. Let's try to explain what this means exactly. Say that we have an object of mass m, perhaps measured in kilograms. Say that x of t is the position of this object, perhaps measured in meters, at time t, perhaps measured in seconds. We can consider the first derivative of this position and denote this as v. This we will call the velocity, and it will be measured in meters per second. We can also write v as dx dt, or we can write it as x with the dot above it. The acceleration, which is measured in meters per second squared, is the derivative of the velocity. We can write the acceleration as dv dt, or we can write it as d squared x dt squared, or we can write it as x with two dots above it. Newton's second law of motion states that if F is the total force on an object, then m times the acceleration is F. That is, m times d squared x dt squared is equal to the sum of the forces on the object. So our intuition here is that the equation F equals ma is really a differential equation in disguise. Let's delve into this in a bit more detail. As one example, I'd like to discuss the concept of gravity. Let's consider a binary system. Well, a binary system is something that we see literally every day. We could have perhaps the Earth, and take a look at how this is attracted to the moon. In a binary system, we just have two objects that are attracted to each other by gravity. Well, Newton's law of gravitational attraction states the following. Any body of mass capital M attracts any other body of mass lowercase m directly to the mass capital M, with the magnitude proportional to the product of the two masses and inversely proportional to the square of the distance separating them. So here if we have a mass capital M, which could be the Earth, and if we have a mass lowercase m, which could be the moon, then there is an attractive force between them, but this force is not only proportional to the masses capital M and lowercase m, it is also inversely proportional to the square of the distance r separating them. This is nice and fancy in words, but let's try to write down some symbols. Another way to say this is F is proportional to the product of the masses divided by the square of the distance between them. That is, F equals negative g times capital M times lowercase m divided by r squared. Here, capital G is some universal constant that is independent of the masses capital M and lowercase m, and of course r is the distance between them. Here now we've introduced a brand new symbol. You'll see that the symbol, which kind of looks like the infinity sign, but is cut off in half, is really read is proportional to. You'll notice that we've changed from F is proportional to capital M times lowercase m divided by r squared to simply writing F equals negative g times that product. G here, of course, is our universal constant, and the negative sign is meant to indicate that the force is attractive rather than repulsive. Let's continue with this example. Let's say that we have a small object of mass m that is relatively near the surface of the Earth. Think of this as perhaps you have a ball in your hand and you simply want to toss it in the air. This ball of small mass lowercase m is going to be attracted to the Earth, but now we have a slightly simpler formula. We can write Newton's law of gravitational attraction as simply F equals negative m times lowercase g, where now lowercase g can be written in terms of the universal gravitational constant capital G, the mass of the Earth, capital M sub e, and the radius of the Earth, r sub e. This lowercase g is just the gravitational acceleration and is equal to 9.81 meters per second squared. Hence, the motion of this object is actually governed by a differential equation. That is, we have here dv dt equals negative g. We won't explain how just now, but one can actually solve this differential equation to find that the position x of t is an equation that you see here on your screen. We can write x of t as x0 plus v0 times t minus 1/2 gt squared. That is, if you take this expression for x and plug it back into f equals ma, that is m times the second derivative of x equals negative m times g, then you'll find that this is a true equation. Here, x0 is the initial position, and v0 is the initial velocity. Again, think of this situation as you have a ball, you toss it in the air, and you want to see what is the path of this ball under the influence of gravity. Now, we've neglected what happens under air resistance. We can consider, let's say, the example of a parachutist falling out of an airplane. As this parachutist falls, the force of gravity, of course, pulls her to the ground, but the parachute causes air resistance, which causes a drag, which then slows the parachutist down. You can click on this link to take a look at the video on YouTube of how this all works out. But for now, let's move on to the mathematics. Because we have air resistance, the force of air resistance really is proportional to the velocity. That is, that the person isn't moving at all, there is no drag from air resistance. But the faster the person moves, the more air resistance there is. So we can say that the force of air resistance is proportional to the velocity. That is, F equals negative gamma times dx dt. Here, gamma is a constant that depends on the shape of the object. Notice that we have a negative because, of course, air resistance is a force that goes in the opposite direction from the velocity. Hence, the motion of this object is governed by another differential equation. Here, remember that we need the sum of the forces. So we have m times a, that is m times d squared x dt squared, has to equal to the sum of the forces. We have negative mg, which is the force due to gravity, and then minus gamma dx dt, which is the force due to air resistance. After dividing by m, we find that dv dt equals negative g minus gamma over m times v. Remember that g, gamma, and m are constants, and we'd like to find this function v, which is the velocity as a function of time. Again, we'll ignore this for now, but we'll see later on in the course that there is a way in which we can solve this equation. We'll find that the velocity at time t is given by the expression that you see here on your screen. But this function involves an exponential, e to the minus gamma over m times t. As t increases without bound, this exponential becomes smaller and smaller. And we find that our velocity tends to a constant number, namely negative mg over gamma. This constant number is typically called the terminal velocity. That is, it's the velocity that really is the asymptotic value that we find as t increases without bound. As a remark, we could have actually found this in a different way by simply setting F equal to 0. That is, the sum of the forces equals to 0 so that all the forces balance out. This is the same thing as saying that dv dt equals 0, and then we could have just solved for v. Now, before we conclude today, let's go back to the example about the US population. Remember our original assumption. Let's denote P of t as the size of the population at time t. We made the assumption originally that the rate of change of the size of the population is proportional to the size of the population. Another way to say this is the derivative, that is the rate of change, dp dt, is proportional to p. We can also write this as dp dt equals k times p for some constant k. Remember that this constant is positive because for now, we're assuming that our population grows as a function of time. Later in the course, we'll see that we can actually solve this differential equation, and we'll find that the population at time t is equal to p of t, which is a constant p0 times an exponential e to the kt. Notice here that p0 is the initial size of the population. However, we found before that this model is a little bit too simplistic. So we'd like to know, can we modify this assumption to be more realistic? Let's do that. Indeed, we don't expect the population to grow without bound indefinitely because we have to take into account that there are limited resources. Indeed, there's going to be limited people, limited space in which people can move out. There are going to be limited resources such as food. So there must be some limiting carrying capacity of the population. That is, our carrying capacity, which we'll denote by n, has two properties. If our population size is less than n, then we expect that there to be an increase in population because the population then would have plenty of resources in which to grow. However, if the population size is greater than n, then we expect there to be a decrease in population because then the population has exceeded its resources. Hence, we're going to assume the following rule. The rate of change of the size of the population is proportional to the size of the population as well as the distance the population is from its carrying capacity. Another way to say this is as follows. The rate of change, which is the p dt, must be proportional to 1 minus p over n times p. Notice that if p is less than n, then 1 minus p over n is a positive quantity. However, if p is greater than n, then 1 minus p over n is a negative quantity. This differential equation is what's called the logistic population model. Later in the course, we'll see how to solve this differential equation, but for now, we'll say that the solution looks like what you see here on your screen. We can write the population size at time t, p of t, as n divided by 1 plus an exponential. Recall that p0 is the initial size of the population, and n is the carrying capacity. Here you see a graph of our solution. On the left, you see the exponential growth that we had when we do not assume a carrying capacity. On the right, you see, assuming a carrying capacity, that the population grows, but it has to be bounded by the carrying capacity. But that was the whole point of the carrying capacity, that we do not want the population to grow too much because of our limited resources. Notice that as time increases without bound, this population size does tend to a constant. It approaches closer and closer to our carrying capacity. Sometimes it'll be useful to consider what we call the inflection point. Here I've written this on the screen as TINF. This tells us roughly the time in which we are halfway to our carrying capacity. By looking at the graph of the logistic growth, you can see that actually this graph consists of a concave up graph as well as a concave down graph. Roughly take your S, the sinusoidal shape, and cut it in half. Everything to the left, that is everything to the left of the inflection point, corresponds to a concave up graph. Everything to the right, that is everything after our inflection point, corresponds to a concave down graph. So our TINF is right smack in the middle when we expect R to be halfway to our carrying capacity. Now let's put all of this together to see if we can answer our original question. Here we've overlaid three graphs. The blue is the US population data that we began today's lesson with. The orange is our best exponential fit, which we found before really is not realistic. The red now is the best fit for our logistic growth model. You'll see that the red seems to match with the blue pretty well. In fact, we can say something about what this graph might represent for the future. Recall that TINF is our inflection point. This tells us roughly when we expect to be halfway to our carrying capacity. Roughly speaking, we expect to be halfway to our carrying capacity somewhere in the next 50 to 100 years. And finally, remember that N is our carrying capacity itself. Here, the graph suggests that the carrying capacity will be around 1.2 billion people. Yes, I know that seems a little bit crazy, but this does say that the carrying capacity of the United States is just over 1 billion people. Thanks very much for watching.